Okay. So, this is a schematic when you are able to resolve both of them and measure the speed of both of them. This is V1, this is V2. The way you measure velocity is that from this spectral shift, you get the value of V and you plot it as a function of time. And of course, if you use simple mathematics, you will see that this will be a sinusoidal curve because you're looking at one of the trigonometric components, either the sine or the cosine component of the velocity is seen along parallel to this direction of the observer. This is the same diagram that we have seen before. Okay, but we have measuring the spectrum from both the objects out here. Okay, so when you have tangential motion, okay, this direction actually gives a tangent. It is actually into the plane of the paper. Okay, if you take this orbit to be parallel to the observer. Okay, then because this is tangential, it doesn't have any component along the line of sight. So both these lines, all these lines will be at their stationary values. Then when you come here, line of A will be blue shifted and line of B will be red shifted. So this particular line, which is perhaps present in both the stars, right? Suppose this element is present in both the stars and we are looking at stars which are very similar to each other. Okay, so both of them have the same set of lines, similar set of lines. It might have some set of lines which are different, some set of lines which are present in both, right? So if you look at the components of the lines, then you'll see at certain instant this line is very strong because it is coming from both, and then it splits into two. One half is blue shifted, other half is red shifted. And then again they combine, they form two lines, the same line, and then again the shift, but now the shift is opposite. The star that had blue shifted will become red shifted, the star that was red shifted will become blue shifted. So if you see, you can see the pattern out here. Okay, what was red shifted has become blue shifted and vice versa. Okay, so this is a very good example of a spectroscopic binary system. In fact, this is not an example, this is a schematic of a spectroscopic binary system. Now, when we observe in reality, you see the velocity curve does not follow the very nice, beautiful sinusoidal curve. That is because your orientation of the plane of the orbit always has angles, there's an inclination angle, there's an orientation angle, and they play their role in changing the velocity curve, and what we see is a result of all those mathematical components coming into play out here. So you have to assume a particular model and then fit the model for the best fit parameters and then obtain the parameters out here. So this is an example where eccentricity is 0.3, the angle of inclination is 30 degrees, and the axis of rotation is 45 degrees. Okay, so your plane is inclined at an angle 30 degrees with the vertical, and the axis of rotation is given by this. Okay, that is 45 degrees. So your total plane is actually something like this, combination of this and this. Okay, something like this. So that tells you that how a velocity light curve will look like and how you have to play around with the model parameters, these values, to get the best value that can fit the data. Now you see, when we have good spectroscopic resolution and good enough timing resolution, Then from this analysis, we can measure the velocity and we can measure the eccentricity. Okay, but understand, we cannot measure the inclination. Okay, so this is something you have to drill. Okay, that when it comes to measuring the quantities of binary parameters directly, we can measure the eccentricity even if we do not see the two objects. From the velocity curve, we can get a measure of the eccentricity and we can get a measure of the orientation. Okay, but it is not possible to get the measure of the inclination angle directly. This always has to be measured using statistical fitting. Now, we can come to the concept of single line spectroscopic binaries, where you do not see the two objects, but you see only one object. Okay, so we can see only one set of spectral lines which are shifting as a function of time. Okay, but there also it is very, very useful to measure these quantities from the Doppler shift, because if you go to the mathematics of the binary star system, remember that we have solved the mass function of the binary star system. Okay, and the mass function is now given dependent on the sine cube of I, right? So hence, by measuring the velocity component, okay, of one star, and by estimating the value of I, the angle of inclination, we can get an estimate of the mass function of the system. And if we can identify one mass from its velocity and periodicity and other parameters, and also from the spectral classification, then we will get the handle on the estimation of the range of the other mass. Correct? So that is why, even if we cannot resolve the companion of a binary star system, we can resolve only the spectroscopic properties of one binary star system and measure the velocity from the spectroscopic observations. Then we can still infer a mass of the companion star. And that is why it is extremely important to observe these single line spectroscopic binaries, such that the binaries companions which are invisible to us, we can infer their properties also. So, this is an example of the velocity curve of the star HD 6619. Again, I'll repeat that we can measure the velocity, the eccentricity, the angle of inclination. Okay, and since we are measuring for both, we are measuring both the velocities out here, and hence the angle of inclination can be inferred. Okay, angle of inclination cannot be measured directly. Okay, now this is a velocity curve of Spica. Okay, understand one thing also very important. These are the points, the circles are the data points which are actually measured. The solid lines are physical models corresponding to the best fit parameter of the properties of the binary system. Okay, so here also you can see that we have measured the quantities of velocity from both the stars independently as a function of time. This is an example of a single line spectroscopic binary. Here you can see the data points correspond to only one star, and it might appear to you that the solid line is actually not fitting the data points. Okay, but basically this is the best fit parameter, such that the deviation of this solid line from all the data points is minimized. Okay, so that is what we call the chi-squared fitting or the least square fitting. Okay, where we try to get a mathematical function such that the total sum of the deviation from all these points are minimized. Okay, so obviously you should come to the conclusion that we need better observation so that we have better statistics in future where we can actually fit this data in a much better parameter with much better parameters.